Okay, I think we can start. Can you hear me?
Okay, yeah, I can hear you. Everyone hear me?
Yes, I can hear you. Thanks. So, welcome everyone to the 8th seminar from Trends in AI Theory Seminar Series. Today, cGAN Chen will give us a talk on his work at unified view of cGANs with and without classifiers. This work is accepted at NeurIPS conference and will be presented at NeurIPS in 2-3 weeks. So we are very happy to have cGAN with us today to present his paper. I'm looking forward to it. So whenever you're ready, the floor is yours and you can start.
Okay. Hi, everyone. I'm cGAN Chen from National Taiwan University. I'm glad to speak here. Today, I'm going to present our work, a unified view of cGANs with and without classifiers. This is a joint work by Zhenliang Li and Shentian Lin. Okay. So generative models are machine learning techniques that learns a target distribution to achieve creativity for machines. They are useful in creative tasks such as molecular generation or picture drawing. And generative adversarial network, or GAN, is a popular generative model which trains the generator and the discriminator adversarially. The generator's goal is to transform a simple distribution, such as a normal distribution, to the target distribution. The discriminator is a teacher, which tells the generator a score, indicating the realness of the generated data. Generators and discriminators are trained adversarially. The generator wants to get higher scores from the discriminator. On the other hand, the discriminator wants to give higher scores for the real data and lower scores for the generator. Conditional GAN, or cGAN, is an extension of GAN which can generate data in a specific category. For example, if we ask the generator to generate an image of a dog, it should generate a dog to get a high score from the discriminator. Otherwise, if the generator generates an image of a hamburger, the discriminator should give it a low score because it is not a dog, like the examples below. We can formulate the objective of GANs by the following. Given some data sampled from a target distribution P with K categories, we want to learn a generator and a discriminator such that the discriminator maximizes the scores for real samples and minimize the scores for generated samples. On the other hand, the generator minimizes the negative scores for generated samples, which means maximize the scores for generated samples. It also called Wasserstein GAN in GAN literature. There have been many conditional GANs proposed in recent years. Most of them have the same architecture for generators, but using different discriminators and loss functions. So here we introduce the 3 most popular conditional GANs. The first one is ACGAN. ACGAN learns a classifier in addition to the discriminator. So the generator needs to optimize the adversarial loss and the cross-entropy loss simultaneously to learn conditional generation. It was the first conditional GAN that successfully generated 1,000 classes on ImageNet. So it is a well-known method. But it is less used now because people notice that it tends to generate easy to classify data. The second one is called projection GAN. Projection GAN is the most popular conditional GAN nowadays. It learns an embedding vector for each class to calculate the conditional adversarial loss, which is exactly the conditional score that the generator wants to maximize. Projection GAN is used in big GAN and is considered a state-of-the-art method of cGANs now. Last one, contrastive GAN or ContraGAN. It applies supervised contrastive learning to learn the class information. Contrastive learning is widely used in computer vision to learn better features. The supervised contrastive learning pulls the instance within each class closer and pushes the instances with different classes away in latent space. And it is applied in ContraGAN and achieves competitive results to ProjGAN. So among the three conditional GAN we introduced, ACGAN is less popular now because it tends to generate easy to classify samples. In contrast, ProjGAN and ContraGAN don't do classification, so they don't have the issue. So we have some questions. Can we use classification in another way to benefit the conditional generation? Besides, while these conditional GANs are designed by different philosophies, can we have a principled way to understand them in a unified view? Furthermore, can we combine them to achieve better results? In this work, we will present a new framework which includes the main concept of the three well-known conditional GANs. The framework inspires a new conditional GAN architecture and achieves state-of-the-art results. So we start our work from an observation of joint probability. By base rule, we know that the joint probability can be decomposed into two forms. The first includes a conditional distribution. The first includes a conditional distribution Px given y and the distribution of labels. The second includes a classifier Py given x and an unconditional distribution of x. These decompositions inspire us to connect the classifier to the conditional distribution by learning the joint distribution in both directions. To model the joint distribution, we parameterize its log probability by a neural network f theta with k outputs, where k is the number of classes. We consider the network an energy-based model, where the exponential of fxy is proportional to the joint probability pxy. Therefore, the joint probability is f theta x given f theta xy divided by the sum of the outputs over all x and y. The denominator here is usually called partition function in literature. And we can train the energy-based model by the maximum likelihood method. As mentioned before, the log likelihood can be decomposed into two forms. So we also have two ways to calculate the maximum likelihood. And here we ignore P of y because it can be estimated by counting. And the other three terms are the focus of our work. Let's first look at the conditional distribution Px given y. By the definition of f theta, the log likelihood can be derived to f theta xy minus log zy theta, where zy theta is a partition function conditioned on y. So the optimization is very hard because zy theta is intractable. Fortunately, there are some works showing how to approximate the partition function. Some of them use functional duality. It allows us to transform the partition function to the form in the right-hand side. And here we introduce a distribution Qy, which is a distribution of x. and HQY is the entropy of QY. The derivation can be found in the appendix in our paper. So now we can replace the partition function with the exponential duality. And we have the log likelihood in the following form. But now there is still an intractable distribution, QY here. So we need to introduce another auxiliary generator, use another network, Q5, to approximate the distribution QY. Then replace the distribution by the auxiliary generator. We end up with a GAN-like objective. Here, the F theta is the discriminator that wants to maximize its output for real data and minimize its output for generated data. And Q5 is a generator that maximizes the discriminator's output. So we can use the standard conditional GAN algorithm to optimize the first two terms. We will discuss the entropy term later. Next, let's look at the unconditional distribution. For the unconditional distribution P theta x, we use a reparameterization H theta x equals to the log sum exponential of fxy and sum over y. Then we can derive the log P theta x to a form similar to the previous case. So here the first equality is by the sum over y, and next is the second equation is by the definition of energy-based model. Then we add a exponential and a log on both the denominator and the numerator. Then by reparameterization H, we can get the result to a form similar to the previous case, like in the conditional version. So similarly, by differential duality and the auxiliary generator Q5, the maximum likelihood of P theta x can also be derived to a GAN-like objective. So we can use a standard unconditional GAN algorithm to optimize the first two terms in this objective. So the last one is, hello?
Can I ask a question?
Sure.
So is what you're describing exactly the same as variational method and lower bounding evidence lower bound, or is it different?
You mean the first part, the first two term, or the whole objective?
The objective here.
Sorry?
The objective. Sorry.
The objective.
Sorry. My question is, the objective is the same as optimizing evidence lower bound, or is it a different objective?
Yeah, in fact, it is because we use the differential duality here, and it's in fact a variational lower bound of the evidence, I think.
Okay, thanks.
Yeah, yeah. This this idea is from the literature in energy-based model. Okay. We just found the form is quite similar to a GAN objective. Yeah. But with an entropy term. So we will discuss this term later. Okay, now we still have a Py given x. So by the definition of energy-based model, we can derive it to a standard softmax classifier for a K-class classification. then maximizing the log likelihood of p theta y given x is equivalent to minimizing the cross entropy loss, just like what we have done or what we usually done for training a classifier. So the remaining thing is to estimate the entropy. Previously, we ignored the entropy maximization in the two GAN-like objectives. And since the entropy of an unknown distribution is too hard to estimate, we choose to maximize the lower bound instead. The first approach is just ignoring the entropy term, because 0 is always a lower bound of entropy. And the second approach is by minimizing the contrastive loss. And by the work cited below, the ICML work, the negative contrastive loss is also a lower bound of entropy. And we leave the proof in the appendix of our paper. So here, we directly use the contrastive loss proposed in contrastive GAN. We have introduced how to model the three objectives for the joint distribution. Now we can combine them together. The loss function includes a conditional adversarial loss, and unconditional adversarial loss, and contrastive loss, and cross entropy loss. We introduce some hyperparameters as the weights of each term. Then we call this framework energy-based conditional GAN, or ACGAN for short. With the ACGAN framework, we can design a more powerful architecture. Note that the network is an energy-based model, so we have K output for the K class as the left-hand side. And the K output can be used to calculate cross entropy loss, conditional adversarial loss, and unconditional adversarial loss. We also introduced the architecture of contrastive GAN to obtain the contrastive loss. So now we successfully get a principal way to combine the loss functions in popular cGANs. By using a subset of the components, ACGAN approximates the three popular conditional GANs introduced before. In other words, we can interpret these cGANs as spatial cases with different level of approximation of ACGAN. And when we keep the cross entropy loss and unconditional adversarial loss, it is similar to ACGAN. And when we keep the conditional adversarial loss, it is a projection GAN. And if we keep the unconditional adversarial loss and the contrastive loss, it becomes ContraGAN. And we evaluate our method on 3 image datasets, including CIFAR10, Tiny ImageNet, and ImageNet. We consider two metrics, inception score and FID. Inception score indicates image quality, and FID measures the distribution divergence between the test and the generated data. We compare our ACGAN to the 3 popular conditional GANs and try different network backbones. We can see that CIFAR10 and Tiny ImageNet, ACGAN significantly outperforms other cGAN methods, no matter which backbone is used. For the FID is the lower the better, and inception score is the higher the better. And for the large scale and high resolution evaluation, we compare our ACGAN to BigGAN and ContraGAN on ImageNet. While BigGAN and ContraGAN both got inception score less than 30 and FID around 25, our ACGAN achieves his inception score over 80 and FID lower than 10. That is a dramatic improvement beyond those well-known methods. So, and here are some selected images generated by ACGAN. So now we can answer the 3 questions. Are classifiers useful for conditional generations? Yes, we found that training classifiers in energy-based model leads to better generators. And can we have a principled way to understand existing cGANs? Yes. Motivated by energy-based model and base rule, we propose ACGAN that covers the most popular conditional GANs, including ACGAN, ProjGAN, and ContraGAN. Can we combine these cGANs to achieve better results? Yes, ACGAN significantly outperforms the other cGANs on 3 benchmark image datasets. And the code is available on GitHub. So, and please check our paper or the code for more details. Thank you. Any questions?
I have a question. So this is the kind of image generator that you can give a class to. How do you compare it with DALL-E from OpenAI earlier this year? It's also a generator that you can give a text description to without using the concept of cGAN.
OpenAI, sorry, maybe I haven't read that one. You say OpenAI have a work that can generate image from text description rather than class.
Yeah, you can generate, I guess, a chair of the shape of avocado, and then it would just generate a chair of the shape of avocado. OpenAI has 2 models. I think DALL-E is too difficult to pre-train, but the other is called CLIP. CLIP is probably the most impactful and actually practically usable concept. It trains by images and the captions found around the images, and then when it's training the ResNet, it also tell the model to pick in a contrasted manner the correct caption. So which is a little bit similar to some of the laws you're using here, although I'm not sure they have a theoretical foundation to use their laws. But CLIP getting trained that way, I think it is not state of art for standard test, but it is state of art for almost every other non-standard test, because it can go into text and out of text implicitly. You have any so you haven't you just compare among the class of GANs? Is that what you're saying? These are models outside of the GANs,
It's the first time I heard that we can generate from the text descriptions. Do they use ImageNet or other?
They use transform. They use GPT-3 like structure. They use transformers. So much.
Well, I mean the image data set.
23 million parameters, and DALL is like 1 billion. No. 12 billion or something. So it is 1,000 times more parameters. It's not using ImageNet. It's using image with captions. Yeah.
Oh, I see.
They source from the internet. So yeah, that's a difference. Yeah, the data set is a lot bigger.
Yeah, and they include two challenging tasks. The first one is language understanding. The second one is image generation.
With clip, it's easier. It's just to you probably use some type of embedding for the text that's already there, and then just you just select which one. Let's say from 1 out of 50, which one is your caption, and train it long enough. And after that, at the end, you discard that part of the model. You just see at the end, you just have the normal ResNet to do their normal other stuff. Yeah, you no longer supply with captions to choose anymore. That's not a real test.
Yeah. I see. Yeah, I will check them later. Thank you for the information. Oh, sorry.
So maybe you can also take those things into a unified framework some other day.
Yeah, actually, we think because our work is mainly just architecture for conditional GANs. So yeah, we have think about any downstream tasks which can achieve by conditional GANs can also apply. We can also apply our method to those kind of downstream tasks of conditional GANs. Yeah, like maybe for data augmentation or any other tasks, we need to model the joint distributions.
Hi, I'm curious about the effect of data augmentation using GAN. For example, if we only have 10,000 1,000 image, and we can use GAN to generate 10,000 image, and then we can use this GAN to again and again, and finally we have lots of images. Can we actually use this image to increase the testing accuracy of a classifier for downstream GAN or not?
Oh yeah, it's an interesting question. In fact, I know several works that try to doing this, but typically for when for some case it indeed improve a little, but from what I have read, it's not a significant improvement. And also when you increase the samples more and more, you samples more and more augmented data, it may not really improve your classification or other tasks, because for now the GANs may kind of remember or we call mod collapse to some specific samples. So although we can generate thousands of data from the generator, but not all the data are really different. Some of them will be similar, and they will not provide helpful information for the classifier. Yeah, but we are also interested in this kind of work as our future work.
Yes, I'm really interested. So actually, if we keep the original data and we can use GAN to generate other data, also they are maybe 10,000 images, but it can be collapsed. More collapse happens, so the effective number may be about only 1,000 or 100. When we combine those the original image, the data set is still increasing, even if more collapse is happening. So I'm curious about whether it's possible or not.
Oh, yeah, I'm not very sure the answer, but from what I know, it's because mode collapse is it's still a big challenge for the generative models. So I think so far it's not a very reliable method for data augmentation, or very strong method for data augmentation, unless we solve the mode collapse problems.
Yes. Also, I have another question about besides mode collapse, there is some possibility that we generate some noise. For example, if we want to generate a number of 2, maybe there are some game they have some errors, so they does not look like 2, or it just look like 1 or something like that. It may generate noise. So once the noise is being added into our training set, maybe the training accuracy will decrease. So is it possible? So since we cannot guarantee that the accuracy of the generated data, whether its label is correct or not, we cannot guarantee 100% accuracy.
Yes, yeah. In fact, we have also done some experiments that use the generated data as training data. We not use it for augmentation. We directly replace the training set by the generated data, and typically it gets although we can sample more data, more generated data than the number of original training data. It's typically the training accuracy is typically worse than the original training data. So
I think this cGAN, your work is on training both the discriminator and generator from scratch, and then Mark, your question is also on that, but now it's nearly the end of 2021. No one should be training from scratch anymore. So both the discriminator and the generator, if I were to be assigning a job, I would pre-train them. And that pre-training would make neither of your question valid. So yeah, if you want to look deeper into what would pre-training change the formula, change the equations, for if you take a clip as a discriminator and take a del E as a generator and use GAN concept to refine them, how much of a refinement are you going to get? That I don't know. You might get some, you might not. If you want to find out, if Professor Lin want to find out, we can work together to look at it. Yeah, really, train from scratch GAN cannot compete with, as far as I know, with these 1,000 times more parameter pre-trained models. But the concept of GAN might still be useful there. Right now, those two passes are diverging, and no one uses them together.
Yeah, in fact, training the ImageNet from scratch take us lots of time and cost for the computation. And I agree that using pre-training is a trend in deep learning research.
MediaTek research can train from scratch or whatever, at least an order of magnitude bigger than normal university groups, if not more than an order of magnitude. Yeah. I think CLIP is very easily doable. DOE, I'm not sure. Maybe approximating there.
Yeah, I see. But in fact, our work, because for pre-training, you still need to, if you use pre-trained model, you should stick on their architectures, right? And for our work, we propose new architectures because so far we're still not sure what kind of architecture is best for the generative tasks, right? The architecture is evolved again and again. From the beginning, we have DCGAN and then ResNet GAN, and now we have BigGAN. And the architecture of conditional GAN also changed. Yeah, also changed from time to time. Yeah, so yeah, I think using pre-trained model is a good idea.
With pre-training, I'm not sure if you read those papers, and before they hit their biggest model, they have to go through, in the past, maybe 4 or 5 smaller models. Now it's like 8 iteration of models. You start with something very small, as small as ACGAN, then add a 0 to it, add another 0 to it, and progressively, most option is to make the architecture stupid and simple. And in favor of eventually you can remember more data. So in the end, the models are so trivial, but they're so powerful. That's a different direction to go, is that let's not be smart with our math. Let's just find out how to use a sponge to remember as many data as possible.
But for generative,
I don't think there is the pre-trained. Is there a pre-trained vision model zoo that people can download pre-trained models? Because we at MediaTek Research, we don't really do vision. We do other stuff. So I don't know. I lost track. Like for NLP, there is a pre-trained model zoo. The largest NLP model you can download has 6.7 billion parameters. Billion. Is there anything like that for vision, for GANs? People train and keep it there for people to use?
I know for classification, there should be some big models, and that's worked very well. But for generation, because people still concerned that if we use a too powerful model, it will simply just remember the training data rather than generate new ones. Yeah, so that's why people don't just use a larger or deeper model for the generative, for the GAN or other generative networks, because they fear that the network will just memory the training data instead of generate new ones. But for from our side, we also have think about how to leverage the pre-trained model, and our intuition is that although the GANs is not, well, I think compared to classification models, generative model is not mature as the classification models. So one of our direction is, can we leverage the pre-trained classifiers, because there are already many large many successful classifiers on maybe ImageNet or any big data set. So what we are interested currently we are interested is, can we leverage the pre-trained classifier into the conditional GANs? And to achieve this, the biggest problem is how we can leverage classifier into GAN. So I think our work, this unified view of cGANs with and without classifier, plays the role that connects a classifier to the conditional GANs. So in the future, maybe we can find how to leverage the pre-trained classifier into these architectures. Then we can use the pre-trained model to help to help generations. Yeah.
Hi, can I ask a question?
Hi, sure.
Why do you choose energy-based model in your work?
In fact, when we because our work is start from the observation that the classifier and the conditional distribution is both a part of joint distribution. So yeah, so at that time we want to find how to model the joint distribution. And yeah, we found energy-based model is a good option that we can connect the classifier and the conditional distribution together. In fact, the idea is from another paper in recent years. I called No More MCMC. And yeah, in recent years, there are several, maybe 2 or 3 works that are about this kind of hybrid models. They use energy-based model as a classifier and a generator to get together. Yeah. And motivated by that work, we found that we can use the idea into GANs and we found this is then we found by using this we can connect the existing conditional GANs together.
Okay. Thank you.
Can I also ask a question? About the performance metric? Is it intentionally selected in a way to reflect the energy-based models, or is it like a generic performance metric? I think it was FID, right?
The voice is not clear, but I think you are asking. Sorry, I think you are asking about the experiment result.
Yes, so this performance metric FID.
Yeah.
So my question is, does it select it in a particular way to kind of capture the energy-based models? So can you please comment on this performance matrix and why does it show the quality of the algorithm, and if basically it is selected in a particular way to reflect the energy-based models, or is it like a general metric that people use?
Sorry, the voice is not clear enough, so I not really get your questions.
Just maybe if you can comment on FID and why is it a good measure?
Whether FID is a good metric for measuring the generation?
Yes.
Okay, yes. In fact, there are some literatures found the problem of FID that, in fact, FID is bias measurements. If you use the same data, if you measure FID between the two two sets that are exactly the same. The FID may not be 0. That is a problem. And also, it doesn't reflect the issue of the maybe recall of the precision of the generation. So there are some new metrics have been proposed, but those later metrics are typically not hard to show the difference between the models because they may be too easy to optimize or too difficult to optimize. So far, FID, I think FID is not a perfect metric for measuring the generated data, but it's for now it's still the most common one we can use. Does that answer your question?
Yes, thank you. If there are any other questions from the audience, please feel free to unmute yourself and ask the question. Okay, I think otherwise we can thank Xian for his great presentation. Congratulations on your paper. And yeah,
thank you.
Thank you.
Yeah. Looking forward to see you in Generative.
Yeah, looking forward to see you. Okay, bye everyone.
Thank you.